So let's dive more into the details. Let's talk about first. We'll give you a couple of examples and how to test a couple of these examples using controller hardware in the loop. So let's talk first about low high voltage write-throughs and what are the emerging requirements under the Rule 21 phase 1 expansion. So fundamentally on this graph, if we want to summarize the requirements for voltage write-through behavior of the inverter, we have 5 critical regions. So on the x-axis we have time, and on the y-axis is actually voltage per unit. Because in the US there are different, this also applies for single phase and 3-phase inverters on different voltage levels, but it can also be completely scaled. So first of all, we have a near nominal regime. So if we are within this band, if the voltage on the grid is within this band, of course this requires complete operation, and that's pretty straightforward. Low voltage region number 1, what we call LV1. Basically, if in case there is a low voltage write-through, we actually need to support this low voltage write-through for exactly 20 seconds. And if the low voltage write-through persists up to 21st second, this is a small red tick here. That's the point at which we need to disconnect. Similarly, there is low voltage region 2 and then low voltage region 3. So basically this specifies the requirement for how long do we have to supply standard operating condition and continue pushing power into the grid. Everything above this region of the high voltage, we have less than 0.2 seconds, 0.16 seconds to disconnect immediately. Same thing, just shown in a tabular form. These are really these 5, and then the 6th region that we are covering. So here the voltages are not. These are actually not normalized. They're within the range of single phase US. But you pretty much have a high voltage region which you're supporting for 12 seconds, but you have to provide momentary cessation or the gate blocking, meaning blocking your gate drives. For low voltage 1, 2, and 3, we have specified voltage levels and the amount of time we have to provide basically mandatory operation in this whole process. Okay, so this is really the summary of all these operating requirements. So now the question is, okay, so how do we test that, whether our inverter is passing or failing? So mandatory operation regions, meaning during the low voltage write-through, we have to provide an average current greater than or equal 80% of the pre-disturbance current. Must trip functionality, meaning if the low voltage write-through persists beyond the mandatory operation region, we basically have to be able to trip immediately between the required time limits. So that's pretty well defined. Okay, but now let's just step back and see how does the controller hardware in loop actually help us do this thing, and how we can actually do these tests and pre-certify our controllers without even going into the high power lab. So the setup that we actually have here, and we will be running multiple examples, we have a small HIL 402 system on our desk. It's our hardware in the loop real-time simulator. On top of that, we have a PV inverter controller directly plugged into the HIL 402, and the schematic here that you can see, this is the schematic of a solar inverter that we are simulating in real time. So just briefly, basically you have a DC source and you have AC source. So with these two parameters you will be able to inject disturbance conditions and check the behavior of your controller and actually precisely measure what exactly is going on. Okay, so this is the schematic, the inverter that we will be running with the controller in the loop, and on top of that we'll show you how you can actually automate the LVRT and high voltage right-through sequences as well. Okay, so let me briefly switch to our Typhoon tool. For the ones that are familiar, I apologize. For the ones that are seeing this for the first time, just a brief walkthrough. We have 4 key applications within our software. You start with a schematic editor, where you're actually defining your power stage. In the control panel, you're actively interacting with the real-time simulation. Script editor is something that you can use Python to automate the testing, and the test suite is something that we will be focused today, which actually allows us to test according to pre-specified grid codes, and today we're focusing on UL1741. So just quickly, this is the schematic that we are simulating in real time. So we have a DC side, simple 3-phase 2-level inverter with LCL filter, and here we have a special block which actually emulates the grid with the impedance and the 3-phase source. So once we compile this, we can just check whether this schematic is working. So just briefly, double check the time domain signals. Okay, well, it's pretty straightforward. We are seeing that we are modulating, injecting the power in. Voltages are fine, currents are fine, so everything is good, meaning our model is actually ready and prepared for test suite. So at this point, we are okay. We can close this tool. We can close the schematic. We can quit the schematic editor, and we are going to our test suite. So when you open test suite, we can, we are going to load a pre-made project just to save a little bit of time here, so you can really get a better sense of all the possibilities and all the capabilities. So if you look here, all the available tests, you can see basically we have photovoltaic maximum power point trackings, multiple tests. We're not going to talk about these today. And then when it comes to grid codes, BDW, IEC, and UL1741 SA. So that's our focus today. And the first step, we're discussing how actually to test against low voltage right through. So this specific project, we have actually 4 tests that we have added. UL-LVRT, anti-islanding, volt-var, and testing for the normal ramp rate. So once we have opened the project, so how do we actually connect and how do we actually specify what this test does? So we double-click, start. We basically start our interactive user interface panel, which is actually going to guide us, step by step through all the necessary actions in order to get the controller tested. So first, we have to specify a model. This is the model that we just had opened. Okay, so this model, when we are loading it now, it's compiling the schematic, preparing the model actually to be run and completely tested. Okay. At the same time, we also specify the settings, meaning we have to set up all the sources, gains, and everything. So we'll just wait here for a second until the compiling process is done. So here we are ready. We also open the settings file, which means setting up all the feedback gains on the HIL system, and we go to the next step. So the next step, we just have to specify what is the rated power. So for this specific application, we're talking about 34.5 kilowatt inverter, and grid voltage, which is actually the RMS voltage line to line of our grid simulator, is 2.8 in this case. This is fully flexible, and you can specify it yourself. And now we are going to the kind of like the most interesting part. there are actually two modes here. We can either go for a pre-certification, which actually, fixes all the tests. These are all the tests that need to be done. Or in the case like here, we can just select a subset of these tests because it takes a lot of time to go through all of these. So for example, first we'll specify that we are testing the power level above 90% of active power. And we have, as we discussed, we have these 5 regions: high voltage region 2, high voltage region 1, low voltage 1, 2, and 3. So, okay, let's, for example, just leave the low voltage 1 region. So we'll just test the LVRT through that, through that first low voltage regime. And on top of that, now, depending whether it's a 3-phase or single-phase inverter, we're testing a 3-phase inverter. It actually requires either symmetric faults, meaning symmetric low voltage right through, where you're injecting, where you're reducing the voltage in all 3 phases symmetrically, or you're looking at all the combinations line to line, where you have dips between A and B, A and C, and phase A, phase B, phase C towards the neutral. Okay. One more thing here, we specify a grid simulator. This is a block inside our schematic which actually emulates the grid condition. We can also pick here different types of reference set points. Basically, how are we going to specify the power of the inverter, either manually, through analog or digital, and we can pick different actually grid impedances, either for stiff, normal, weak, or customize it. Go to the next level, and now this is basically the profile, how we are going to be cycling our dips on the voltages. So here, voltage at point of common coupling, we basically have 80% nominal voltage. We can specify the hold time, the delay, and the recovery time, and also we can pick number of repetitions, meaning how many times do we want to cycle the inverter through this. Just before we start the simulation, we can choose to wait a little bit or just go pretty much all the way to the end. We can finish, and then boom, that's done. So we have now completely defined the tests for low voltage right through that are now ready to be executed. So the execution button is just we run these tests automatically. Since it takes some time, which we don't have at the moment, while the LVRT is running, I can actually just open a report that was automatically generated just before this webinar. Basically, this is automatically generated report. What we actually have, okay, this is not the right one. This is what I wanted to show you guys. So basically, first part, we have test parameters specified, meaning, specify description of all the variables, rated power, grid voltage, what is the nomenclature, what are we using here, and then we start immediately into the section number 3, detailed report. So for low voltage region 2, LV2, operation mode. So this is mandatory operation. So basically now we're going to be, we have cycled our power through the profile, and we are seeing actually what the results are. So voltage at this point of common coupling was reduced to 60% with hold time of 10% in this specific test, and we have average pre-disturbance current calculated. So this is all per unit. So let's basically look at the report. So immediately we see here the first graph actually shows us normalized RMS values of line to earth voltages. So we can we can clearly see the low voltage right through profile. These small spikes that you see here, these are the voltages on the impedance of the grid. At the same time, what we are looking at here are basically line currents and power. So you immediately see as we are having a voltage dip, the currents are actually going up, trying to maintain the operating point, maximum power point, and continue injecting the same amount of power. Figure 4.1 gives us zoom in at the beginning of the low voltage ride-through event, where we can actually see the grid voltages. So we had 1 per unit nominal voltage, and then all of a sudden we have this dip down to 60%. We see a little bit of disturbance here. This is due to basically the injected currents from the inverter. At the same point, we can also see how we are exiting actually from the low voltage ride-through. That's basically the end of the cycle. Yeah. And same thing. We can look at the normalized. All this is provided. All this is provided directly in the report. We can look at the normalized RMS values. Normalized RMS values of the line currents here as well. Take a look at the voltages. So now basically we are repeating this test multiple times, and all these graphs are automatically captured from the simulation and automatically generate this report, which now allows us to basically automatically qualify our inverter controller, without doing any kind of power tests in the lab. Okay. Of course, this is, fundamentally, this is just a shortened version of LVRT. We have cycled just through, one specific condition, low voltage condition 1, and where we had to provide the mandatory operation. For the full test, you have to basically specify all the parameters for all the symmetric and asymmetric faults, and go through the complete cycle. So this is an example report that was generated from automatically from that low voltage ride-through test from the project. Okay. Similarly, there is basically another way to do as well low high frequency ride-through, similar to like low voltage ride-through. Basically, here just a little bit slightly different definition of the frequency regimes. We have a near nominal regime where we basically have to provide mandatory operation, and then we have one high frequency region 1, and then high frequency and low frequency region 1. So summarized basically in this table, again in high frequency region 1, we have to provide mandatory operation for 299 seconds, and if the low voltage, the high frequency ride-through prevails, then we have to disconnect at before 300 seconds. Similarly, low frequency ride-through 1, we have to provide mandatory operation. Again, for 299 seconds, we have to ride through this event and not disconnect, not to jeopardize the grid. And then if it maintains for longer than 299 seconds, then again we have to disconnect. So setting up the project for low frequency, high frequency ride-through is very similar to the LVRT. So we're just not going to do it here. We're going to skip immediately to something which is really interesting and really nice, unintentional islanding.